Okay, this is lesson 1 in the magnetism topic. The magnetism topic is in 2 parts. The first part primarily deals with permanent magnets, electromagnets, that type of thing. And the second part looks at what's called the motor effect and using magnets in electric motors. So in this lesson, we're primarily going to be looking at these first ideas in our checklist. Now, talking about the checklist, this is something you should notice that in your pack, whenever you have any pack, it always starts with a checklist. And once you've completed the pack and you've done the corrections, you should complete the checklist. So you rag rate the checklist to make sure how confident you feel about each of the topics. On the second page, you have a list of facts. So these are the things you should know. And on the side here, we have the things you should be able to do. So again, you should be checking that you know all of these facts and that you could do any of these things. Okay, so we're going to start with lesson 1, which is on magnets. And by that, I mean on normal permanent magnets, which are what most people think about when we say magnets. And so you have at the top, you write the date of the lesson. And then we're looking at the first task, which is to draw a circle map. So we need to draw a circle map, and we're going to fill that in with whatever you know about magnets. Now, for example, you might know that magnets have a north pole and a south pole. So whatever you remember from your Key Stage 3 lessons, you're writing in here. Around the box, you're writing down any applications that you might know of with magnets. For example, using a fridge magnet to hold pieces of paper on the fridge. They're used in loudspeakers, they're used in electric motors, but you might have other ideas. Now, this circle map is something that you can add to as you go through the lessons once you learn new things. So now the first thing we need to do is just to establish some facts about magnets, some of the basic facts about magnets. So the first thing we can say is that magnetic force, it can be attractive like gravity, so pull objects together, but it can also be repulsive. It can force objects apart. Every magnet has got two poles. The first one is called a north-seeking or a north pole, and the other one is called the south pole. Then in terms of magnetic force, we know the rules of the magnetic force are that like poles repel, unlike poles attract. Okay, and one other thing I can add in here is that magnetic force is a non-contact force. So magnets don't have to touch for them to feel an attractive or a repulsive force. So magnetic force is a non-contact force. Okay. So that's what magnets are, but we need to think what magnetic materials might be. So a magnetic material is any material that feels a non-contact force when it's near a magnet. So that typically is a piece of metal like iron. Now it's not a magnet, but when you put it close to a magnet, it feels a force. So magnetic material is a material that feels a non-contact force when near a magnet. And there are 3 magnetic materials that you need to know about. Those are iron or steel, cobalt, and nickel. So those are the 3 that you need to know that are magnetic materials. Now what that means is things like copper used in wires or aluminium used in tin cans and cans for Coke or any other sort of fizzy drink. The aluminium is not magnetic. So things like aluminium will not feel a magnetic force close to a magnet. The force between a magnet and a piece of magnetic material is always attractive. So when I've got 2 magnets, the force can be either attractive or repulsive, whether the poles are the same or different. But when it's a magnet and a piece of magnetic material, the force is always attractive. Okay, now in the next task, you needed to explain what was going on in this picture. And there was a short YouTube clip put on the lesson on Show My Homework that shows this working. You need to include a description of the forces acting on the paper clip in your answer. Are these not contact or non-contact forces? Okay, so there is a non-contact force pulling the paper clip down. So the paper clip feels a force downwards due to gravity, and this force is called weight. Okay, now the paper clip floats in the air, so as the paper clip doesn't move, the forces are balanced. So what that means is it also feels a magnetic force upwards equal to the weight. So what's happening there is there's the force downwards, which is the weight of the paper clip pulling it downwards, and there is an equal size force upwards, which is a magnetic force that's pulling it upwards due to this magnet that's above it. Now, magnetism is a non-contact force, so it means the magnet can exert a force on another object without touching it. It's very surprising, to me at least, that people aren't more surprised about things like magnetism and gravity. So these are forces where objects can influence each other, can pull another object without touching it. In the case of gravity, it's the earth that is pulling an object, for example this paperclip, down. It's attracting the paperclip downwards, even though the earth is not touching the paperclip. So it's a non-contact force. Likewise, a magnet can have a non-contact force, as it does here. And the way that we explain that is we explain that in terms of the magnetic field. So the magnetic field is something that exists around a magnet, and this is what allows the magnet to put a force on an object that's not touching it. So we can draw what this magnetic field looks like, and the rules are pretty simple. The magnetic field, it always follows an arc, so it goes round from the north to the south and then passes through the magnet like that, but we don't see it because it's inside. So the arrow is always out of the North Pole into the South Pole, like this. And we've got another one here. And another one out here. And then that one will be going round and eventually coming back in here. This one the same, coming back in here. So it looks like this. So what we can see is the lines are really close together when we're close to the magnet, and they're quite far apart as we go further away from the magnet. So what do these show? So the magnetic field lines show the volume of space around a magnet in which a magnetic material will feel a force. So this is showing us if I place a magnetic material here, it will feel a force. And what do these magnetic field lines show? Well, they show us, number one, the shape of the magnetic field. They show us, number two, the direction of the field lines. and it's always from north to south. So the lines come out of the North Pole and they go into the South Pole, and they show us the strength of the magnetic field. So even though I don't have any numbers written on this, what I can say is if there are more lines close together, that means the magnetic field is stronger. And we see that happens when we're close to the magnet and the lines go further apart, so the magnetic field is weaker as we go further away. Okay, so the next task you needed to do was, using the video to help you, you needed to give a step-by-step set of instructions to investigate the magnetic field around a bar magnet using this video and the PowerPoint to help you. Here I've got a bar magnet, I've placed it on my piece of paper and I'm going to follow my instructions. So the first thing I need to do is I'm going to draw around my magnet. That's so I can take it off the paper if I need to and put it back where it was. And I need to mark, this is the north side here, so that's my north side. There, okay, so I place that there. And I'm going to put my compass here. And the instructions then say to place, once I've placed the compass near the magnet, I place a dot on either side of the arrow. So let's go a little bit closer so we can see this. So I'm going to have a dot here and a dot here. And I take that away and I join that with an arrow in this direction. And then put my compass back again, and this time I'm going to start it from where the last one finished. So I only need to put in one dot, which is here. And again, I draw an arrow and put in another one. Takes me to here. And I continue this process over and over again, gradually building up my picture of the magnetic field. And I do this on both sides of the magnet. Once I've completed plotting these points on both sides of the magnets, you can see that I've started to form the shape of the magnetic field around my bar magnet. So the magnetic field is looping round from the north side to the south side on both sides of the magnet. As we get further away, the lines become further apart, and we see the lines of the magnetic field are very close together at each of the poles. So this is where we expect the magnetic force to be greatest. If we put another magnet close to either of the poles, we expect to feel the largest magnetic force. If we put it further away, the lines are further apart, so the magnetic field is weaker, so the force will be weaker. The magnetic field loops round. Now in reality, what happens is it would come through the magnet and join, so it forms a closed loop. But obviously we can't put our plotting magnet inside the magnet, the plotting compass inside the magnet itself, so we can only plot the points that are outside. Okay, the other important thing to realize is that all the arrows are pointing out of the North Pole and they're all pointing into the South Pole. So, going back to our pack, these were the instructions that we followed. We drew our results. What direction should the lines be in? The magnetic field lines loop around the magnet, and here's the important point, from the North Pole to the South Pole, always from north to south. Where is the magnetic field strongest, and how do you know? Well, we can see it here. The magnetic field is strongest close to the magnet. This is shown by the magnetic field lines being close together. So that's what we see here. The lines are very close together, and here the lines are very close together. So that's where our magnetic field will be strongest. Okay, now the next task, we have to watch the video on permanent and induced magnets and create a double bubble map comparing permanent and induced magnets. So I'm going to have my permanent on this side and induced on this side. So make sure you've watched the video, pause this video if you have to go back to watch this video, and that you've completed your version of the double bubble map and then compare it to mine. The double bubble map completed. So we've got the permanent magnet on this side, the induced magnet on this side. So the permanent magnet, it has its own magnetic field, whereas in the induced side, it only becomes a magnet when it's inside a magnetic field. So there has to be another permanent magnet. The permanent magnet doesn't lose its magnetism. The induced magnet, it'll lose most or all of its magnetism as soon as you take it out of the magnetic field. So if you take away the permanent magnet, this will lose all its magnetism. And the thing to notice is the induced magnet, it's always attractive force with the permanent magnet that makes it. So it's always attracted to the permanent magnet. Now, why does that happen? So if here I've got a permanent magnet north and south, and I put that beside a piece of material made from steel or cobalt or nickel, what happens is this is the south pole on my permanent magnet. So when it induces the magnet, it makes this a north pole and that a south pole, so that there is an attractive force. If the permanent magnet had been the other way around, with the north pole on this side, then the induced magnet would have the south pole induced on here. So the force is always attractive when we induce the magnet. They do have some things in common. Both have a north and south pole. And in both types of magnets, the like pole repel, unlike poles attract. So remember, the induced magnet, it's always attracted to the permanent magnet that generates it, but then it becomes a magnet. So if we introduce another magnet, then the usual rules apply. Like poles repel, unlike poles attract. Now, we know that normally we can use a compass to navigate, and the compass needle, without any other magnet, the compass needle should point north, so we can always find our direction using a compass. The reason why this is because the Earth itself is magnetic, and it's the core of the Earth that generates the magnetic field around the Earth. Now, we have to remember that the north pole of the bar magnet in a compass, that points to north. So that means it's pointing to the south pole because opposite poles attract. So if I was to draw the magnetic field of the Earth, what it would look like is like a bar magnet. It'll have the same shape with the magnetic field lines going round the Earth like this. However, what we'd see is that the lines are actually coming out from what we normally call the South Pole and going into what we normally call the North Pole. So the lines, the magnetic field lines, are coming out of the Antarctic and they're going into the Arctic. So in actual fact, whereas this is the geographic North Pole, is where we have the Arctic, and the geographic South Pole is where we have the Antarctic. In terms of this being similar to a bar magnet, this is actually the South Pole. So the magnetic South Pole, where all the lines are going in, is in the Arctic, and the magnetic North Pole is in the Antarctic, where the lines are coming out. So it's the opposite route around to what we might think. Okay, that's the end of lesson 1.